So yesterday we talked about decision trees, and today we're going to keep going, but saying, what if we had more than one tree, or how do we improve the performance of these? So we're going to go through a bunch of these different methods, basically to deal with what we call ensembles of models. So ensemble, just in terms of English, it's not used a lot, so you might not come across it. The simplest meaning of it is just group. But it's kind of like a collaborating group of things or people, right? If you know theater, right, like a theater troupe, you go to see a play, um, and when you talk about the people who are the actors in that, um, that's usually called an ensemble. Or if you think in classical music, like we have a string ensemble, right? So you're gonna do like Mozart's, string quartet thing. That's for, string instruments. You have a violin, a viola, and a bass, and a cello. That's string ensemble. It's a bunch of different parts, and they all work together to form the one thing, which is the piece of music, right? So just in terms of what the word means, if you haven't heard it much, that's what that means. And a string ensemble is actually a really good model because it's important when you've got those four instruments, right? That each of them plays, different types of different notes, right? So one of them is really low and it's doing the bass part, and one of them is really fast, but they're all forming together. So they're all kind of experts in some part of the piece of music. But when they come together, they create this really strong piece of music, which is the ensemble, right? And it works together. So actually, what we're doing here is trying to get our machine learning algorithms to do that, right? So the decision tree is our base. In this case, actually, it's not required to be a decision tree, but for now, we'll just say our decision tree is our base thing, like one of the instruments, and then we're trying to train a bunch of them to do different parts of the data in a way that's robust and helps us get a better model, right? And the ensemble is the net effect of all of these. So that's a general idea. But now mathematically and kind of technically, how do you set that up? And what works and what doesn't? Okay, so start with these ensemble methods. Right, we start with this first idea. Is there a perfect algorithm? And the answer is no. Just jump to the spoiler alert. There's various pieces of kind of wisdom and like unofficial rules in science and math that tell you this kind of stuff. So this kind of very famous quote, which I assume is from this statistician, but you never know if it's always from the right person. The statement is all models are wrong, but some are useful, right? Which is a thing to keep in mind, right? That no matter how hard you work at it, no matter how well you're fitting the data and predicting it, maybe it's getting all the answers right on your test data, there may be data points you've never seen before, right? And so everything you're doing is an approximation of the reality, almost always, right? But if it's a useful approximation and it's good enough for our purposes, then it's great, right? Like Newton's laws of motion are wrong, right? They're just wrong, right? There's all kinds of stuff they get wrong. They don't deal with gravity. They can't do orbits. But in our day-to-day life, they're good enough for everything, right? So that's a model that's useful, but wrong. And Einstein's relativity is less wrong, and we're not quite sure in which ways it's wrong or not. No one's ever found a particular thing it's wrong at, but it doesn't explain everything because it doesn't explain quantum physics. So that's a very useful method that's also wrong, but we don't even know how, right? So in our case, when we're learning a decision tree or a neural network, it's never going to be perfect. That's just the idea to keep in your head. This other thing that I was looking up last night to try and find it because I was like hearing about it as this no free lunch theorem. It doesn't completely apply to what we're talking about, but you can read about it if you want to find it interesting. The main essence of it, and people have mathematical descriptions of this. It's just a statement in English, it's like there's no free lunch. It means you don't get anything for free. You can't get something really good without putting any work into it. That's just a life aphorism for people, right? But in machine learning and statistics, people have tried to have a mathematical description of what this means in a sense that no matter how good your function is, your fit or your predictor, there could always be some data that breaks it. And assuming that there's an infinite universe or that all the variables are uniformly distributed, no matter how good your model is, there's just as much data that would prove it wrong. It's just you've never seen it before. So some people debate whether this is true or not, and it actually doesn't really apply. It applies in a mathematical pure thing, but not in reality. So it's interesting, but not essential. But it comes to the same idea that there's no such thing as a perfect algorithm. Maybe you just haven't seen enough data, right? So the idea is that we're not trying to build a perfect thing. We're trying to build a model that has regular behavior, that's predictable, that doesn't overfit, and because we wanted to do well on the test data that has been held out. So it's not just overfitting, it's generalizing. I guess we could say also generalizable. But this idea that it's somehow optimal, you always got to be suspicious of that, because if something is optimal or perfect, that means you're making an assumption about the data. And if that assumption is true, then you're fine. But if it's not, then your data is useless. Just like we had with our map estimator last week. If you remember that, we can say, here's a distribution, and we assume that, the parameters of this distribution have a Gaussian kind of prior to them, so they have a certain probability distribution, and under all those assumptions, we can optimize it and find the perfect estimator, right? But if the data is not actually Gaussian, and the way that it behaves in the world is slightly different than that perfect probability function, then our model is just wrong, right? Even though it's optimal in this imaginary space. Okay, so one way we try to make a problem less bad, if we know that it's overfitting, right? We've talked about regularization a couple times. The last class we had this cost criterion. Was that last class? Or was that this class? I think it was last class. For optimizing the decision tree. We've talked a little bit about other times you're adding some, like in MLE, we're adding other penalty parameters to the function, right? So at some point we had adding an x that was kind of squared on itself. That's one of these penalties. So basically some way that says if you're optimizing to maximize some function, or say minimize some function like a cost, and you add some other element to it, which basically penalizes a certain setup, like maybe too many parameters, like too deep a tree is what we were talking about yesterday, right? Or you could have too many variables that have high numbers. You could penalize those so that your algorithm doesn't overfit as much, and you're basically regularizing it to basically reduce overfitting. So when you say reduce generalization error, right? Generalization error, if you have high overfitting, then you'd have high generalization error, right? And generalization, right, just means that you've done really well on the training data. Then you should also do well in the test data because it generalizes the data you've never seen before. That's all they're talking about there. When we get to neural networks, we'll have other types of regularization, so you can do things with the structure of your model. So in neural networks, you've got all these arcs and connectors that were going across the model. If you just kind of randomly delete some of them when you're training, this essentially forces the model not to overfit because it's constantly trying to adapt to which ones are missing. And that's called dropout, and that's kind of regularizer as well, because it forces it not to overfit by basically hampering it every time it's learning, right? But we'll talk more about that. Today, what we're talking about is a regularization approach, really a whole class of approaches called ensembles, where we're doing this thing like a classical ensemble, string ensemble, where we're going to have different models collaborating together to give us a better answer than one model alone can give us. Makes sense. We're up to 45 people now. All right, so I've already said this then. So the basic idea of ensemble is rather than just training one model, we're going to train multiple models, and we're going to train them on parts of the data at a time and then combine them. So how do you split up the data? How do you define and train each model? How do you combine them? These are all questions or decisions, and your answer to each of these, basically every instance of an answer to all these questions gives you an algorithm, right? So there's a lot of algorithms. Basically all the different ways you could do this, you give you a different algorithm. We're going to talk about the most important ones that work well, but you can invent your own once you have this pattern. Right, so here's that point I was making. I'm talking about it in terms of decision trees today, but once we have this here, we can kind of refer back to it later that the ensemble doesn't have to be decision trees, right? So you think about an ensemble essentially as we have a bunch of models, and the data is coming in here, and then the results going to come out here. We're going to have multiple models, so today we're going to talk about everything's going to be a bunch of trees, and the way we grow the trees affects that. But there's no reason you have to do that, right? You can basically say that some of your models are neural networks, or some of them are logistic regression or SVM. So you could combine the results and basically vote on who does well, right? So this general idea works to everything. But it's particularly easy to understand with trees, so that's why we start there. Okay, so a couple different, this question of how do you split up the data and how do you combine them together? There's kind of three main ideas that you can use that we'll talk about. And you'll end basically applying different versions of these will give us some of these different actual algorithms that we'll talk about. I guess the most popular of these would be that and that, because they're kind of most general and used everywhere. Okay, so when we were talking about sampling and subsampling and cross-validation, I don't know if I used the word bootstrap, but we talked about sampling, selecting, or sampling points from a training set with replacement, right? So remember, over say we've got our earns, and we're trying to sample how many we're taking out. We've got red balls and we've got blue balls in the data set, and we want to say, let's sample one out, and then afterwards, do we put it back or not, right? So if we're doing it with replacement, we put it back in the data set. So that means, we literally could have the same data point sampled out twice. And sometimes that's going to add bias, but it actually can be useful because then you're always sampling from the exact same data set every time. So we're going to use this, even though sometimes we're going to get duplicates. It means that everything can be completely independent because you know that the data is basically it's not affected by your previous draws, right? Because if you don't do with replacement, say you just got lucky and you picked like 10 red balls out of this in the first 10 draws. Now you go to this thing, this is actually, a different X because it's an X that has almost no red in it. So the distribution is changing. If you're doing with replacement, the distribution of X is never changing. So it helps with stability that way. So the first method that we use for ensembles is called bagging. It's basically this kind of bootstrapping or sampling with replacement. And we're going to learn the classifier. So it could be a decision tree. So we're going to use decision tree here on the data set, just like we did yesterday. So we learn a decision tree on the data set, and we save that. Right, so that gives us model 1. We've got some decision tree. And then we're going to, but when we train it, we train decision tree on not all of n, we're just going to train it on some of n, right? And n is like a subset of the full data set, right? And then we're going to draw multiple subsamples from it, but with replacement. And so now we'll build another model, which will end up being a different tree after we learn it. In this one, let's say this is sample N1, this is sample N2, and N1 and N2 are both kind of random subsamples of the original data set, but they're different, right? But they might overlap, right? So if we say N is the entire data set, that's not a very good circle. N is the entire data set. N prime is going to be some subset of it, but N prime 1. But these two data sets may overlap. We don't know or care how much. They're just samples of it. And we're going to learn multiple of these, right? And then we're going to learn a whole bunch to give us a bagged classifier. So this is called bagging. And I don't know why they called bagging, but they had to come up with something. Where you're basically taking a bag of some of the examples and then training on it and keep going. So what's the advantage of this? It reduces some instability because you're kind of having classifiers that are specialized on certain areas of the data, right? So this classifier, D1, doesn't know anything about data points that are outside its circle, right? It never saw any of these data points, right? So it's going to be a specialist in this. But if you learn enough of them, you're going to cover a lot of the space and essentially learn specialized models of different subsets of the data. But since they overlap, there's some redundancy. So it kind of just works, even though it's using randomness to kind of work well. So that's the first idea of bagging. I guess we'll see how these get used. So we'll just go through these three concepts and then we'll see ways that they're used for actual algorithms. So boosting is the second one. So this one can get you, this has got quite a claim, you don't see people make very much, that it can give you arbitrarily high accuracy. So it's a way to make your classifier actually better, but using sampling. Typo on slide 10. Do it in a way that improves it. So how could we do that? If you think about learning your first tree, right? So this is our class number 1 that we did on some subsamples, same thing of the data. Now we want to say, well, what's the accuracy on all n, right? We could test this on all the data, right? And so now you'd have a set of your data points, right? And you'd have some score, right? Of how well it does. Are we using accuracy? Yeah. So that was a 20, right? So it's going to do well on some and bad on others, right? So the idea of boosting is to say, well, when you take your second data set, make sure that you take a new data set that has more of the bad data points, right? So of the ones that it's doing badly, the first model, you want to use more of those in this data set, right? So basically, you're training the second model to do well on the things that, in particular, model 1 did badly on, right? So we're trying to maximize information gain, but on the previously trained classifiers, right? So we're trying to basically improve on that. So it's like if one of you, tries to search for some record in a big stack of papers, and you get it right. The ones that you get wrong, the leftover stack, you give that to the next student, and then they focus on that. So they might be focusing on different aspects because they're focusing on the ones that you got wrong. Right? So model 2 is going to be learning a completely different type of pattern on the data because it's going to be working on the ones that model 1 found hard, right? And maybe like with our data thing about people and income and jobs, right? Maybe model 1 is focusing more on income and education, and it gets a really good categorization of what job people end up in. But maybe 10% of the data it got it wrong, and so model 2 is going to be basically looking at all the ones it got wrong plus some others, and it might focus on something different like area code or something, and not really look at money because it's got to basically compensate for model 1. Another concept we have in here then is weak learners, I think. we'll talk about that somewhere. Maybe not. The idea is that you don't need to be very good at this then, right? Because you know that the next model is going to fix what you messed up. It's going to improve on the things that your first model did badly on. You could even have a very simple model, right? So we're talking about a weak learner. We're saying that each of the models here could be smaller. So you could have a decision tree and limited to depth 3 or 4, which would be very shallow, rather than letting it go to 10 or 20. And so, I mean, the reasons we do that, anybody think of any reasons why? Because why would you want to use worse models? You could always use the best model. Do you have any thought on why that would be? And so Dallas got that. So we want to avoid overfitting. Yeah. So I mean, the whole point of doing this is we want to avoid overfitting, right? Because we want to have the first model is going to be good at certain data points, and the next one's going to be focusing on things it got wrong. So we don't want to overfit on the ones that it did wrong. But in a sense, this yeah, the this approach of like having each, because imagine we build like 100 models then, right? We said arbitrarily high accuracy. If you have more and more models, you're just basically going to do really well. Eventually you would overfit, right? Because maybe the last model is just going to memorize that one you got wrong that doesn't fit the pattern at all, right? So if we force the learners to be weak, basically very simple models, then none of them are going to be fitting the data perfectly. They're all going to have quite a bit of errors. But when we combine together all their answers, we'll get a better joint answer. So yeah, it's basically reducing overfitting is really the best way to think of it. So these are a very simple example just to make it concrete. So say we have our data set D. We're going to divide it into 3 different subsets. And we're running any classification algorithm, but we say we'll run decision trees on the first data set. And so we run this classifier and it does something, and it has a certain accuracy level. And it has like, a true false count, how many it got correct and how many it got incorrect. And so we train our second model, D2. We take half the points that C1 got correct, right? And half that it got incorrect, right? So it might be that it only got maybe only 10% of its things were incorrect, but we're going to make it so that the second classifier, half of its data is the ones it got wrong. So it's not only the ones it got wrong, but it's heavily weighted by that. And then we train that classifier on that. And then for the third subset of the data, we basically take the data points that they both got wrong, either one of them got wrong, and use that as our data set. And maybe we also do, 50% or 30% of random points, and train on that, right? And we can keep going, right? So if we have, 100 models, then they're all basically going to cover very different methods of it. So this is very useful as an algorithm. This, what we described here, is just kind of a meta algorithm, because it just says, use whatever classifier you want, select the data this way, so you could fill in the parts of that algorithm I show, just this approach here, in a specific way, and then you get a particular implementation. So the most famous one, I guess it's probably 30 years old or more now, Adaboost, but many other things have been built on it, was this called Adaboost, named after Ada Lovelace, I assume. It was like the first computer programmer in the 1800s, a woman who programmed for like Lord Byron or Babbage and his machine in Europe. So in general, we're talking about this being, we're going to have some weak learners, so we can define it kind of in general. We have some function that we're going to learn a class, given some data, and we're going to have k of them. And it has to be able to give us some value or confidence in its classification output. And then we have to find a way to combine these together, right? So we're going to have multiple classifiers. You still have to say, how do we combine their answers to give us our final classifier, right? If I go back to my output here, my design for this thing, there's a question here, right? What's the function that takes all of these in and then gives you the result, right? It could just be a sum, it could be a max, it could be a weighted majority. So all the ways you could combine these are all valid ideas. Basically, what Adaboost does, it says for any data point that we're looking at, we use a majority. We weight each classifier by how good it is at its job, and then we basically say, does it think is the data point should be in class 1 or in class 2? And if it's been a model that worked well or it dealt with a lot of data, then it will be weighted more highly. Then it'll give you the final answer of what your classifier should be. Sophia's got a question. Are we doing this so that at least one classifier is able to predict correctly some subset of data that wasn't predicted correctly by some other classifier with regards to boosting? It's more than that. So the question is, are we trying to make sure that, we've got our areas of data here, right? Where's my Venn diagram? We're hoping that, D1 is going to do well on this part of the data, and then D2 is going to do well on this other part of the data. And so at least somebody's covering all the areas. So that's one part of it. But another part is to make sure that there's multiple ways to look at overlapping data, so that we get different opinions, right? Because the first model could be wrong about these data points. It's just been trained on them. Now, when you have multiple different opinions, you might actually learn that classifying these data points comes you to a different answer. So we want robustness, generalization, basically by focusing on different subsets of the data. We're forcing the model to be more diverse and not overfit, because it's going to have to specialize in different parts of the data, and we're doing it randomly because we don't know the data. So we'd rather just say, just randomly do it using, well, not random. This one's not too random actually, because it's using the performance of the other models, right? So it says take the ones the other ones are bad at and do that. What we also found then in other algorithms, which we'll do next, is that adding randomization makes it even better. You don't want to just rely on fixing the errors of one model and then training on those. You actually just want to throw in randomness, because maybe that first model was good at some data points, but it was just lucky, not because its model is really good. So randomness is going to be another big way to modify this. So there's a pseudocode of this Adaboost algorithm. So we have some initial weights. Every model, every data point, our data point gets a weight assigned to it, so they're all kind of uniform. And then we train this weak classifier, so we can train our decision tree. We basically are sampling weights, sampling data points based on how well they've been picked so far. And then once we have a classifier, we can compute its error rate. So how likely is it to get some data point wrong, given what has been trained, right? So we can run it on our validation set and kind of compute this error. And we use that to get this alpha. So the alpha is what they're going to use to kind of weight how important a data point is for training. And you're using this information theoretic model of it. I forget why they came up with that particular function, so I can look that up. But we've got our error here, right? So we want to basically say that we're getting an error rate. So what's your positivity rate? It's like your ratio of correct to false, right? So it's kind of like we were looking at with the ROC curve and precision, right? So how many of the data points did you get right versus how many you got wrong, right? Because epsilon k is your error rate, so 1 minus is your kind of success rate, and then you're turning that into a log. So we use that as a weight, and so you see what's happening. We're weighting here is that we got our label now, creating a distribution. we're looking at the classifier's answer. And so for this data point I, we're going to say how good is the classifier currently, and then we're going to weight it by how important this data point is. And K is the model, right? So these are the weak learners. So for the kth tree, tree 7, now we're going to say what's the weight we should use in the next tree, right? So for the next tree, when we grow it, what weight should we give all the data points? So we can re-weight them and say, oh, you know what, we're doing really badly on certain points because they had a high error rate, and now we're going to up their weights a bit. And in the next iteration, once we spawn a new decision tree, it will be more likely to sample those data points. And it'll learn a model that's trying to fit those ones better. So it's kind of, it's not just using this pure sampling idea, it's using all the data points but weighting them. And so you're kind of, I guess if you've got your data points here and you've got maybe your accuracy of one model, the next time through you want to go on some other model, right? And then the next time through you want to go on that one. And then you kind of just keep trying to fill all the gaps that each model, each new weak learner is trying to fill in the gaps of what the previous one is doing well on, so that you learn with better variety. Does that make sense? You can try it out. This will be one of the ones we'll be kind of trying to look at. I don't have to look and see if we're using Adaboost directly, but we're using a boosting algorithm for the next assignment that combines these, uses these ideas, but it also combines a couple other ideas. So that's the first part, which is about all the ways we can sample the data to build ensembles and combine the model results to build these ensembles. The next part is about randomness, which is the other major component that makes ensembles work quite well. So a random forest, which is really one of the probably most popular thing to do with decision trees. So when we talked about, decision trees are a core kind of algorithm that are well known and can be used on their own in some cases. But in most cases, especially machine learning and big data and like lots of stuff, you're using some version of a random forest rather than a decision tree. Because a decision tree just grows a single tree and it kind of might overfit to that, or it might not have enough flexibility to kind of learn the best pattern. And like we said, it's very expensive to learn a perfect decision tree. So what we do is just we're going to learn a whole bunch of them as a random forest. It's a forest of trees, right? And we want to basically reduce the variance on the decision trees, right? So that we make sure that the answer we get is more stable and more reliable. So this one does not use boosting, but it does use bagging, right? So we talked about boosting, it's not using that, but it's using this bagging idea that we're going to randomly choose a subset of the data with replacement. So every tree has the ability to see all of the data. And we're going to learn a bunch of classifiers independently on those, and then average them together to give us one main classifier, right? So it's very simple. What else do we do? Yeah, so that's the main idea of a random forest, basically doing many decision trees with bagging as the rule for resampling. So this was, I guess, only 2001, so it seems like it's older than that, but it's 20 years old, but that doesn't seem that old these days. So it uses bagging. You can learn a bunch of trees. So I always say T like 100 is kind of a good start, 100 trees. Usually if you have like 300 or 500, improvement is not that much. Beyond something like 100, 150. But it also depends on data size, right? If you're doing like genetic data, this would not be enough. But if it's something like the census data or something with a reasonable number of like 30 or 40 features, 100 might be reasonable. So the other part we have to do is how we're going to pick these features for training the tree, right? So if we remember from yesterday from the CART algorithm for decision trees, every time you're learning a tree, you can pick any feature and you kind of compute the best cost difference for every possible feature and subset, and then you pick the one that optimizes that, right? In that kind of makes it more expensive, right? To compute. So in random forests, we're going to add this one additional thing is that we're going to sample a subset of the features that it can actually use, right? So for every data set, say we've got our original data set of size n, right? And so we've got tree one, it's going to learn some subset, and it's going to have, like we said, n prime data set, which is less than a subset of the full data set. But we're also going to use some set of features, which is less than the entire set of features, and randomly sample that too, right? And so the second tree is going to be some other set of things, but it'll be a different set of data points and a different subset of the features. And we kind of continue in the same way, right? So not only are we limiting now the data subset, but also the features we could use. We do that randomly. So that really pushes the variety for each one, because now each tree is limited. Maybe this tree doesn't have access to the income feature that we've been talking about for census data. So we have to figure out how to build the classifier using all the other information. So that's really going to reduce overfitting and give you more generalization because they have to learn a completely different model. Right, and so it tries to learn that particular subset of features we've been given, and it's really a great method. Outperforms a lot of stuff. It's a very general approach that works well. We said we didn't have boosting, but if you added boosting, you can add boosting by altering the way the n samples are chosen, right? So you could just say that for tree two now, we're going to use the ones that all the previous trees have done badly on, and use that to weight the sampling, and now suddenly it's a boosted random forest, and that usually helps even better, although it might like slightly more likely to overfit, right? Because every tree now is going to be trying to perfect the previous ones. A random forest itself doesn't overfit because you can just add more trees and it gets more general, and it's quite powerful that way. So in some ways, it's like the simplest, most powerful machine learning algorithm. It isn't always as good as neural networks, but it's simpler than neural networks and much cheaper to run. And it's fully universal, which we'll talk about again other times. That is basically any function you want to learn, it could learn it. Sophia's got a good question. Are all the subsets disjoint? No, right? So what does disjoint mean? Did I have with replacement here? So we're using, oops, wow, what happened? We're using bagging, right? And so we said bagging is sampling with replacement, right? And so by definition, that means that the data sets are not, they're not necessarily disjoint, right? So we have the entire data set, N1, N2, N3 could be disjoint from it, but they're all subsets of this, and we do it with replacement. So anytime we use sample points, we could resample them. So they are not disjoint sets, but they're all subsets of the full data set. So what else are they doing? Easily tunable, there's no tuning, just this T, how many trees is one of your parameters. I guess there's some other parameters. What else? What other parameters could there be? Anybody can think of others? The whole random forest algorithm. Yeah, so right, so size or depth of each tree, right? So does it stop at 10 and then it stops? Any other ones? Yeah, number of features per tree, right? You don't want it to be, it definitely should be like more than two, probably more than four. Um, Size of the subsets, yeah, for sure. So the the n, the size of each n, do you do it like maybe you give each tree, 20% of the data each time, but when it's randomly deciding which 20%, if you give it 50% of the data, then they're all going to like learn the same things very frequently. But it depends how much data you have. But if you have a very small amount of data, maybe you do want to train it on 70%. You just have a small number of trees, right? Um, if we're going to have a large number of trees and a low number of trees, so they kind of those interrelate with each other. What else? You could also have branching. So we're assuming branching is binary, um, usually two, but it could be higher. So each tree could split on multiple ones. Um, I think those are the main ones. Good. Relatively fast to train, robust. Yeah, so we lost our interpretability, right? So remember when we have a single tree, we could read off all these rules and say, oh, it means, x is less than this and f2 is greater than that. Now every tree has a story about how to divide up the data, and the joint answer is all of them combined, so we can't really interpret it that well. You could try to come up with average rules across them, but it's hard to interpret. Basically, any good model in machine learning is usually hard to interpret. People often complain that neural networks are hard to interpret or impossible to interpret because of the way they're set up. And then they'll say, oh, decision trees are better, but only single decision trees are better. Random forests, which is what you would actually use, aren't really much better. I mean, theoretically, every tree has a story here with all these rules, but how do you combine 100 trees, random stories together? Right, so this is on what we'll call batch data, not streaming data. We're going to talk about that next. So all the data has to be available at the beginning, right? Because the way it's training um, using CART, that's an important part. So when doing a random forest, initially each of these is being trained as a decision tree, right? So to learn that single tree, you have to look at the entire data set you're given, compute the cost function, and do this, deciding to split. You could even do pruning and all that together, and then learn your decision tree, and then move on, right? So you have to have all the data up front. If new data arrives, you can't just update it. But we're going to fix that very soon. Okay. I just had a slide here with performance comparisons. This is maybe not the best place to have it. Just to give you a sense, because we've seen some of these now. What are these numbers? This is from the Murphy textbook, so you can see it's a photograph. Okay, so the rank here is how often was it like, how often was that algorithm the best uh, at at the data set? You give it a bunch of different random data sets and randomize it and cross-validate it and say how often did this algorithm win or not. And then boosted decision trees. I guess that was boosted decision trees. So random forest is right up there at the top of his table here. And this is neural networks, but not deep neural networks. So the classic old neural networks is just a single simple one. So it wasn't working as well. SVMs is the one we're going to talk about. So those are all in the future. KNN we've done, it was not as good, right? Because it's kind of limited to that neighborhood structure. All these tree-based ones were the best approaches, right? So bagging just decision trees, random forest, and then boosting with decision trees as well was the best on this particular data set. But a decision tree on its own, without boosting or anything, was actually worse because it was maybe limited to that. and then logistic regression, naive Bayes. So we've kind of gone through a bunch of these now, and we're essentially going to add other ones. Well, we've seen all of these as well. I don't know what that one means. We'll have to look that one up. Scikit-learn also has some other ones, so we'll come back to this kind of plot later, but at least seeing structure of how, if you think about our data set and data points, and this, if you ask about different types of test questions, this is a kind of test question I often have, which is like, okay, I'll give you some data set points and say that we're classifying something, and I'll show you a bunch of outputs of different classifiers and ask you, which algorithm did this, or what parameter of that algorithm is more likely for that one, because they have different ways of behaving, right? So here's our, we've done nearest neighbor, we've done decision tree, random forest, Adaboost, naive Bayes, and these ones we'll do next week. So what are we seeing here? So the red points, I don't know if you can't see the colors, that's going to be unfortunate, but I'll draw around. These are class R, and these other ones here are class B, and they match the same kind of patterns here on the rest of the figures. So nearest neighbors, I don't have what the rows, there's 3 different data sets, is classifying the data points either to be in their class or in the other one, and you can use the distance from your neighbors to give you maybe a soft kind of feeling, like is it as confident about it or not? And so is it getting it correct? But it's kind of overfitting, but it's doing well by getting a lot of the classes. Decision trees, right? Remember, the decision trees are essentially cutting straight lines into the feature space, right? So the features here are just X and Y, right? Feature 1 is X, feature 2 is Y on this actual plot, right? So there's only 2 dimensions. And so decision tree, right, creates cuts about like all the data points that are greater than X equals, have X greater than 2 or Y less than 4, right? That's how it divides up the space. So it'd get a classifier that looks like this. And these ensemble methods basically are having many trees averaged together. So they're still going to be blocky, but they can have something that gives you a mixed pattern, right? Because a bunch of trees agreed this one was better. And so now it's on that class, right? And if you think about naive Bayes, essentially we're building a very linear, like weighted model of all the different points. So we're trying to fit a line through space, but it's soft based on probabilities from multiple dimensions. So to give you a feel for how each of them are really dividing up space differently and why some might do better than others, right? Obviously, something that's nonlinear and has better ability to capture any arbitrary shape is going to give you a more powerful method, but it might be more complicated to compute how to do that, right? Which is why that's what happens. And neural networks aren't even on here, but neural networks would look more like this, but with more kind of complexity.